Welcome to the Data-Driven Organizations module. This module introduces how modern organizations use data and data science to make decisions. The introduction section describes the content of this module. The module introduces a basic vocabulary for talking about data-driven decision-making. You'll learn to distinguish data analytics from artificial intelligence and machine learning, or AI/ML, and describe how they all support data-driven decisions. You'll be able to identify the layers of a data pipeline and the actions that are taken on data as it passes through the pipeline. You'll be able to list the types of work that a data engineer or data scientist do when building out a data pipeline infrastructure. And finally, you'll be able to talk about 3 strategies for building modern data infrastructures in a data-driven organization. The objectives of this module are presented across multiple sections. Each section will be presented in its own video. The module wraps up with a sample exam question. This section introduces modern approaches to making data-driven decisions. According to Gartner, through 2026, organizations will accelerate their investments in data and analytic services by 45% to become more data-driven and digital. So what does it look like to be data-driven? When it comes to making decisions in your life, how do you decide where to eat or where to live? You probably use a mobile app that gives you personalized recommendations. 20 years ago, you would have relied on options such as asking a colleague or comparing information from websites. But now, people regularly rely on apps to support large and small decisions. Those apps use data science to analyze available data sets, find insights, and suggest possible decisions to you. Like you, organizations have become more data-driven over the last 20 years, evolving their use of data from reporting on their operational past to predicting their best options for future success. One thing fueling the data-driven evolution is the explosion of richer and more abundant data from websites, mobile apps, and smart device technologies. The data science behind data-driven decision falls into 2 main categories. The first is data analytics, and the second is artificial intelligence, or AI, and its subfield, machine learning, or ML. The primary distinction between the 2 categories is how data scientists use them to arrive at their results. Data analytics is a broad term that describes the systematic analysis of large data sets, also known as big data, to derive insights. For example, consider the question, which factors are most important to the selection of a restaurant? The data scientist would hypothesize about the data variables involved and then use statistical methods and programming techniques to derive results. Traditional data analytics uses rule-based logic to make predictions. With ML models, a data scientist can automate an application's ability to actually learn and improve the quality of its predictions. For example, an ML model could use data about what diners actually do after receiving a recommendation to refine their future recommendations. The ML model learns by getting more and more examples. ML models might also be able to find relationships among the data that would be much more difficult for a human observer to hypothesize. The more high-quality data that you can provide, the better the predictions that ML can produce. Here's a simplified example to distinguish a traditional analytics approach from an AI/ML approach. You have a large and growing data set of animal images, and you want to feature only the dogs on your website. To use traditional analytics, you would need to write logic to define features that make a dog a dog. Think of trying to code all the different characteristics that 2 dogs might have while still being recognized by us as dogs. And what logic would you use to avoid the cat fitting into your model? With ML, you would train your model by showing it a lot of pictures that are labeled as dogs and letting it learn to identify new unlabeled pictures as dogs. For many business scenarios, your organization might use both data analytics and AI/ML as part of a unified decision-making strategy. This slide highlights a simple example. A retail business uses data analytics to analyze revenue per customer and segment customers based on spending. Then the segmentation is used to offer higher levels of customer service to customers who spend more. That same business might use an ML approach to uncover factors that influence customer churn and then make changes to improve customer retention. You can categorize analytics into these 4 increasingly valuable but increasingly difficult to derive types: descriptive, diagnostic, predictive, and prescriptive. The volume of data needed, amount of compute and storage required, and complexity of the data science all increase as you move from descriptive to prescriptive decision support. The explosion of richer data sources has coincided with the availability of much more powerful compute at lower costs than what had been available. Cloud-based infrastructure and evolving cloud offerings have increased resource flexibility and lowered the technical complexity required to derive higher value insights. The easier it is to make predictions, the more an organization can extend data-driven decisions into additional scenarios. The increasing use of data and the application of AI approaches is recognizable when you interact with online systems as highlighted on the slide. The navigation system in your phone is a great example of how large amounts of varied data are brought together to personalize your navigation experience. All that data presents challenges as well as opportunities. Organizations must decide how to store the data and account for both traditional structured data organized as rows and columns, as well as unstructured data such as images, documents, and handwritten notes. Organizations also need to manage the security of all that data they're collecting and ensure their solutions can scale to handle the volume and type of data to be processed. The trade-off of collecting more data in hopes of fueling more decisions or providing greater accuracy has to be weighed against the cost and speed impacts of managing and processing all that data. Another consideration is how quickly you can act upon the data. As the slide highlights, the business can derive the most value from data when it is fresh and can be used immediately. For example, to prevent a fraudulent credit card transaction. As data ages, it loses its ability to inform proactive decisions and becomes an asset to take action after the fact. When deciding what to keep and how long to keep it, an organization should think about whether they have the capacity to process the data within the timeframes that maximize its value. The trade-offs you need to consider are reflected across your infrastructure choices. Choose components that provide the best value for the decisions that those components must support. Balancing cost, speed, and accuracy is at the core of building the infrastructure that an organization needs to support data-driven decisions. Here are a few key points to summarize this section. Data-driven organizations use data science to inform decisions. This includes data analytics and AI, along with its subfield, ML. Traditional data analytics relies on programming logic, while AI/ML can learn from examples in data to make predictions. This makes AI/ML good for unstructured data where the variables are complex. The rapidly increasing availability of data, coupled with decreasing cost of technology, increases the opportunity for organizations to make data-driven decisions. A data pipeline provides the infrastructure to turn data into insights and make data-driven decisions. This section introduces the basic layers of a data pipeline. At the most basic level, any data pipeline must be able to bring data in, store it, and provide the means to work with the data to derive insights. As the data engineer or data scientist, it's your job to build the pipeline. Often, this will include exploring and experimenting to get to know the data and the best way to derive value from it. The number of variations and options to create a data pipeline are broad. The key to designing an effective decision-making infrastructure is to start with a business problem to be solved or decision to be made. Then, build the pipeline that suits that use case. The cloud makes it easier to start up different infrastructure to serve different use cases. An organization doesn't need to invest in an infrastructure that tries to serve all business needs with a single database, server, or technology stack. For each use case, start with the end in mind and build the data pipeline that supports it. The infrastructure layers that you need to build include methods to ingest and store data from the data sources that you have identified. You need to make the stored data accessible for decision-making. You must also create the infrastructure to process, analyze, and visualize data by using tools that are appropriate to the use case. To do this, you will need to understand the nature of the data and the intended type of processing and analysis to be performed. Looking at the pipeline from the perspective of the data that travels through it, the pipeline must support the ability to discover details about the data and how it fits or doesn't fit your intended outcomes. You might start with a hypothesis and use business intelligence or BI tools to discover more information about the data and then experiment and see where it takes you. Data might need to be cleaned or normalized. For example, you might need to rectify inconsistencies between two data sources that you're merging. Or you might have a data source that hasn't been well maintained or validated at its source. You need to prepare the data before it's viable for analysis. Data will almost always be transformed as it moves through the pipeline. This might include modifying the format to support an analysis tool or replacing values, for example, zeros in place of nulls. You might also augment the dataset by filling in gaps or enriching it with additional information. For example, you might add calculated values to be used during analysis. You might also add metadata to categorize and catalog data. Data wrangling is a term that is used to describe the ways in which data is manipulated and transformed from its raw state into more meaningful states for downstream processes or users. Within each layer, or as part of transitioning between pipeline layers, you might perform these tasks to prepare data for the desired outcomes. Some types of tasks can happen in multiple places across the pipeline. They can also be performed together as part of a single process. For example, in traditional data science architectures, the extract, transform, and load, or ETL process, takes data from one source, performs some type of transformation on it, and then loads it into another location where the analysis is done. As you learn about different scenarios, you will see these tasks performed at different points in the pipeline, using different services and methods dependent on the use case. The tools that you use and the way you perform these tasks will differ based on characteristics of your data, the business problem that you're addressing, and the methods or models that you're applying. Another key characteristic of deriving insights by using your data pipeline is that the process will almost always be iterative. You have a hypothesis about what you expect to find in the data, and you need to experiment and see where it takes you. You might develop your hypothesis by using BI tools to do initial discovery and analysis of data that has already been collected. You might iterate within a pipeline segment, or you might iterate across the entire pipeline. For example, in this illustration, the initial iteration, number 1, yielded a result that wasn't as defined as was desired. So the data scientists refined the model and reprocessed the data to get a better result, number 2. After reviewing these results, they determined that additional data could improve the detail available in the result. So an additional data source was tapped and ingested through the pipeline to produce the desired result, number 3. A pipeline often has iterations of storage and processing. For example, after the external data is ingested into pipeline storage, iterative processing transforms the data into different levels of refinement for different needs. In this example pipeline, the data set to be ingested is a CSV file that contains structured data. A developer uses a utility to compress the file, then uploads the file to an S3 bucket for storage. The data science team who will analyze the data can use S3 select statements to directly query the data in Amazon S3. Here are a few key points to summarize this section. The data pipeline provides the infrastructure for data-driven decision and includes layers to ingest, store, process, and analyze and visualize data. Data wrangling refers to the work to transform data to prepare it for analysis. Processing is typically iterative. The business problem should drive the pipeline design. This section introduces the responsibilities of the data engineer and data scientist roles to plan and manage a data infrastructure. To build the correct pipeline, the person responsible for building the pipeline needs to ask a lot of questions about the nature of the data and the intent for its processing. You can classify the questions broadly into data engineering questions, which are mostly focused on getting the data into the pipeline, and data science questions, which are mostly about what you're trying to get out of the data. Examples of data engineering questions include things like, does the organization have data that addresses this need? And how is it stored? Examples of data science questions include things like, what can the data tell me? And how will I evaluate the results? In the remainder of this course, you'll learn how the answers to these types of data questions lead you to select components and build pipelines that provide the appropriate infrastructure for data-driven decisions. Here are a few key points to summarize this section. Data scientists and data engineers both work with the data pipeline, and depending on your organization, some tasks might be performed by either role. But generally speaking, the data engineer is focused on the infrastructure the data passes through, and the data scientist is focused on analyzing the data in the pipeline. Both roles need to ask questions about how the data meets their needs and iterate on their answers and design as they learn more. This section introduces strategies that an organization can use to make the most of its data infrastructure. If you go to work for an organization that aspires to use its data as a strategic asset, you will likely spend time adapting more traditional infrastructures towards those that are designed to better support data analytics and AI/ML. AWS advises its customers to approach this type of data infrastructure along 3 strategies: modernize, unify, and innovate. Modernizing the infrastructure gives an organization the agility it needs to respond quickly to changes in the business landscape. The practices listed here are actually applicable to any modern application architecture. But in this course, you'll look at them through the lens of data analytics and AI/ML use cases. AWS uses the term undifferentiated heavy lifting to refer to the IT tasks that take time and resources but don't really relate to a business's core value to customers. For example, managing hardware or patching operating systems. By migrating to the cloud, an organization can reduce its focus on administrative activities and instead focus development resources on business functionality. The cloud also makes it easier to start up different infrastructure to serve different use cases. An organization can choose the best set of tools and resources for each business problem. They can also experiment with new environment types or services without committing to resources long-term. Another advantage of using cloud services is the ability to use purpose-built data stores rather than using a single type of database to serve all needs. You can choose a data store that matches the data structure and scalability required for each use case. Together with purpose-built data stores, use loosely coupled components so that you can choose services that are designed for a targeted purpose and modify or scale them independently from each other. This greatly increases the flexibility of the infrastructure. One of the most important and most challenging strategies for successful data-driven organizations is to unify data to create a single source of truth. This means moving from siloed databases for each group of users to a data lake. A data lake brings all the data together and democratizes access. Control of data moves away from a centralized IT team where users must request data. With modern data strategies, users can directly access the data that is relevant to them and build their own visualizations. Users can run queries directly against the data in the lake. But your infrastructure should also support movement between the data lake and purpose-built data stores that are needed for specific use cases. Moving to this type of data structure often requires significant changes to the cultural aspects of who owns the data and the governance needed to maintain the single source of truth. As noted in an earlier section, the exploding availability of data and the lower cost of applying AI make it possible to incorporate AI and ML into more decision-making. Organizations that take advantage of this can drive value in new ways and adapt to changing business needs more proactively. But it takes conscious effort to reframe business problems as prediction problems and experiment with ML models. One trend in AWS service features is an increasing ability to apply an AI/ML type of functionality without as much overhead or required experience as more traditional ML infrastructures. For example, Amazon SageMaker Studio provides fully managed ML infrastructure and a no-code visual interface for business analysts. Amazon Redshift is a data warehouse service, and one of its features, Redshift ML, helps users to create, train, and deploy SageMaker models using familiar SQL syntax. Being a data-driven organization means culturally treating data as a strategic asset and then building capabilities to put that asset to use. not just for big decisions, but also for everyday actions on the front line. Organizations that can put their data to work to make better, more informed decisions can respond faster to the unexpected and uncover completely new opportunities. Here are a few key points to summarize this section. Organizations that want to become data-driven should modernize, unify, and innovate. This means moving to cloud-based, purpose-built services and reducing operational overhead. It also means creating a single source of truth for data and making data available across the organization. Organizations should innovate by finding new value in their data with the use of AI and ML. This section summarizes what you've learned and brings the Data-Driven Organizations module to a close. This module introduced data-driven decision-making and how data analytics and AI/ML can support decision-making. You learned that both data analytics and AI/ML can help with predictions, but AI/ML does it by learning about the data rather than by using programmed rules. You've learned about the 4 main layers in a data pipeline: ingestion, storage, processing, and analysis and visualization. You were also introduced to the type of actions that are taken on data as it passes through the pipeline. For example, cleaning and transformation. You heard about the types of concerns that a data engineer or data scientist might have when building out and using a data pipeline. And finally, you learned about the modernize, unify, and innovate approach for building modern data infrastructures. Here is a sample exam question for this module. A traditional retailer with a relatively small online presence recently decided that they need to expand their online presence to increase sales. After a major marketing push and investing in IT infrastructure to support increased online transactions, quarterly results show that online sales results are far below expectations. The business wants to find ways to improve the poor online sales performance. Which action represents an appropriate first step to address the request in a data-driven way? What are the key parts of this question? Here are the key words and phrases in the question. The question implies the need for some type of analytic solution based on the desired outcome of improved sales and the desire to address the request in a data-driven way. The other key consideration is that the question asks for the first step. Now let's look at the answer choices. The possible choices include A, develop an ML model that analyzes customer comments to determine where customers are unsatisfied. B, use A/B testing to provide some customers with a new UI that is designed to simplify the purchasing process. Then compare sales results from the old and new UIs. C, use a business intelligence or BI tool to analyze sales data for the previous 2 quarters. Then generate a hypothesis as to why the online sales are not in line with expectations. D, analyze the total revenue per customer and create customer segments that receive different types of offers based on their segment. Based on the keywords that were identified in the question, which answer is correct? We'll pause a few seconds before discussing the correct answer. If you need more time to consider the choices, pause the video. The correct answer is C. Choice A, develop an ML model that analyzes customer comments to determine where customers are unsatisfied, might be appropriate if the retailer believes that the cause of poor sales is related to customer satisfaction. Choice B, use A/B testing to provide some customers with a new UI that is designed to simplify the purchasing process and then compare sales results from the old and new UIs, might be appropriate if the retailer believes that sales are low because customers are having difficulty making purchases through the older UI. Choice D, analyze the total revenue per customer and create customer segments that receive different types of offers based on their segment, might be appropriate if the retailer believes that low sales can be attributed to the way that different customer segments shop on their website. Each of these answers, A, B, and D, represent ways that the organization might gather and analyze additional data depending on their hypothesis. But the first step should be to work backwards from the business problem, poor sales, to form a hypothesis, and then build a data pipeline to collect and process data iteratively. So choice C is the correct answer. That concludes this module. The Content Resources page of your course includes links to additional resources that are related to this module. Thanks for watching.
Welcome to the Elements of Data module. This module introduces elements of the data that you need to be aware of to design a data pipeline for decision making. This introduction section describes the content of this module. The module introduces a basic vocabulary to think about the data sources that will feed your pipeline. You will learn about the 5 V's of data and how each of them influences the choices that you will make in your data pipeline. The objectives of this module are presented across multiple sections, each with its own video. The module wraps up with a sample exam question. The questions on this slide were introduced in the Data-Driven Organizations module. The questions are directly relevant to the data characteristics that are discussed in this module. Answering these questions means understanding the 5 V's of data. This section identifies the 5 V's of data, which map to the questions that a data engineer must answer to design a good data infrastructure. The 5 V's are volume, velocity, variety, veracity, and value. Consider volume and velocity together because you will make infrastructure decisions about how to collect, store, and process data based on the combination of how much data you need to ingest and how quickly you will ingest it. Variety and veracity both relate to the data itself. What type of data is it, and what's the quality of it? Data engineers and data scientists will transform and organize the data based on its variety and veracity to make it useful for analysis. Value is about ensuring that you are getting the most out of the data that you have collected. Value is also about ensuring that there is business value in the outputs from all that collecting, storing, and processing. To work backwards from the business need, let's look at value first. The value that you want from your data will drive all of the pipeline decisions that you make. The data strategies that were highlighted in the Data-Driven Organizations module are reflected in these strategies. First, decide whether it appears that you can derive the desired outcome from the data sources that you have. Determine if you need to find, buy, or generate other data sets to meet the need and whether it will be feasible and cost-effective to get the data. Next, match your infrastructure decisions to the volume, velocity, and variety of the data to be collected and stored, and find the best balance of throughput and cost for each use case. Where is it worth spending more to move faster or acquire more data for the decision making? After you decide to invest in the data, maximize the ability of your users to draw out insights. This means reducing the time that you spend focusing on operational or administrative tasks rather than directly focusing on business value. This also means making it possible for users to discover all the data that you already have that might be relevant to a new business problem. It's also critical that you put governance in place to maintain the trustworthiness and accuracy of your data.